Hello, welcome to this session of engine condition evaluation testing using the pressure transducer. First test with a pressure transducer is going to be exhaust gas pulsation. It doesn't get any less intrusive really than placing the pressure transducer into the tailpipe of the exhaust. Switch the pressure transducer on, allow it to cycle through each range, because whilst it's doing that it's calibrating, so at that point it's important to have the test port open to atmosphere. In the pressure transducer kit we've got the exhaust sensing hose. Clip that on. Select range 3, because range 3 is the lowest pressure rating on here. It's plus or minus 5 psi, which is plus or minus 0.345 bar. We'll connect that to picoscope channel A, BNC cable, BNC connector to BNC on channel A of the scope. And depending on your exhaust arrangement, you may need to bung one of the tailpipes. You'll see on this van here that we've got a twin outlet tailpipe. So we'll bung one of them and then insert the tube into the free tailpipe. That way we'll sort of boost, if we can, the pulsations. That'll just improve measurement resolution. And ideally, if you can, try and support the pressure transducer as well. So we use a gear tie. Hook that up onto the exhaust bracket just so that that's not bouncing about, especially if we've got an engine that's running uneven for whatever reason. So carrying out the test for exhaust gas pulsation, we'll follow the guided test. So this is the automotive menu. Scroll down to pressure transducers. It's a WPS 500X pressure transducer, and we want exhaust tailpipe, and this will be exhaust pulses, engine running. So you click on that, that will open up the guided test, that will describe the process, but more importantly, it will set the scope up, so time base, probe setting, voltage range settings, that'll all be set for you. So we hit the start button, transducer's in the exhaust, start the engine, we'll capture the pulsations. Okay, we'll pause the software and we'll just run back through the buffer. Initially, not very exciting, but if we use the scaling feature here, and we'll upscale, factor of 2, 3, 4, 5, you can see there that we have uniformity. We have pulsations from the exhaust system. If we pull the rulers down here, we can see that reasonable consistency on this engine, no issues, no misfires, no combustion anomaly. I'm happy with those pulsations. So, quick tip here, if we right click and click on reference waveform, we can duplicate that. So now we have a duplicate of exactly what's on screen. We can run Pico again. We'll leave everything set as it is, and what we'll do now is we'll disconnect number 4 injector. So we've introduced a fault on the vehicle, and we'll compare waveform like for like. Pause that. As you could hear there, that was certainly misfiring. And here we have our current waveform against our uniform waveform. So the light blue, that would be our engine running, pulsations are uniform. The dark blue, that was our waveform we've just captured, the current one. You can definitely see that there's a repeat pattern there. There is an anomaly, there is a reason for concern with the pulsations in the exhaust. Following on from our exhaust gas pulsation measurement, we've identified that there is a anomaly in the exhaust. Where do you go next? Well, is it compression? Is it ignition related, injection related? We could go relative compression. That will eliminate a number of hopefully mechanical issues. So if we follow the guided tests now for relative compression on a diesel, and we'll find that of course under the automotive menu. So automotive, it's under charging and starting systems. Click on relative compression and then select diesel. Of course, that opens up the help file. That will also have the connection diagram, tell you how to connect. We'll use the 2000 amp current clamp because certainly on diesel you'll see peak inrush current of up to and maybe over 1000 amps 1 kiloamp. So again, when we set the current clamp, we'll switch on, press and hold the 0 button because that will then light up red. So this will now remain on until the internal battery fails. If you just switch on without pressing the 0 button, it lights up light green. So after, I think it's 6 or 8 minutes, that will switch off. We want the 2000 amp mode, and we want to attach that around the current clamp, sorry, not around the current clamp, around the battery negative lead. Whichever lead, we'll go for negative on this vehicle because it's easier to get to. It's a single lead going back to a battery negative terminal. Just ensure that you have the arrow the right way around, the orientation of the current clamp. Think of the starter circuit, the current leaves the battery positive terminal, through the circuit and returns back to negative. We'll minimize the help file, the guided test, press the start button. Everything is set for us, time frame, input range, the probe setting. All we have to do now is crank the vehicle. So I should say, sorry, that we have the fuse removed for the volume control valve on the diesel pump, so this vehicle now will crank but not start. Okay, so there we have it. If we review the data, we're looking at the peaks here because the peaks denote the compression, if you like. If you think about the load on the starter motor, as the piston rises on the compression stroke, the current draw from the battery increases. So we'll look at the peak current and relate that to peak compression. Again, as you'll note with all of these tests that we do, it's all about uniformity. We're looking for 4 even pulses, 4 even peaks, whatever it may be. We can see there on this vehicle, we've got good compression. What we'll do, we'll take a reference waveform here. So we'll close the zoom. We'll do the right click, which is the quick and easy way. Click on reference waveform and click on A. What's happened now is that's duplicated our relative compression waveform. So we'll run the same test, only on the next test now, we'll lower the compression on a particular cylinder and see how the two compare. Okay, so following on from our previous relative compression test where everything was okay, I've introduced a dummy glow plug to cylinder 4, but a longer than necessary glow plug, and also then a compression hose as well. So in effect now we've lengthened or increased the volume within that cylinder. So we are going to lower compression. It's a little bit of a cheat, but it'll enable us to do a relative compression test with a lowered compression on one cylinder, and then we can review the results. Nothing's changed in the software. We keep the same guided test. We've kept our reference waveform on screen of our good relative compression test results. We'll crank it over now and capture, hopefully, a cylinder down and how that's reflected in the current from the starter motor. Okay, there we have it. We'll just separate these two so you can see, and we'll zoom in. If I just pull these rulers down here, so the dark blue is the current waveform we've just captured. The light blue was our previous one. I think we can safely say that every third peak, we've certainly got a compression down, or we've got reduced current. So the effort on the starter motor on one of the 4 cylinders has been reduced because the compression is not so great. And then on the remaining 3, it's business as usual, the compressions are fine. So in this scenario, we would stop would we stop pursuing using the pressure transducer? Next step would be to put the pressure transducer in that offending cylinder and find out why we have a compression loss. If we'd had good pressure, so a good relative compression, we could safely say that compressions appear normal from a relative compression point of view, and that we could pursue looking at other avenues as to why we've got this instability in the engine. We'll now move on to, well, first one, the next least intrusive, if you like, is crankcase pressure. We'll put a pressure transducer into the dipstick tube and just have a look at what activity we've got in the crankcase. The next test is crankcase pressure analysis, or the measuring the pulsations in the crankcase, because we know as the piston comes down the cylinder, certainly on the power stroke, there will be an element of blow-by gas. The velocity of the piston coming down the cylinder as well. Ultimately, all this pressure ends up in the crankcase, and we can measure that. And again, it doesn't really get any less intrusive. If the exhaust gas analysis there was minimal intrusion, the absolute maximum we have to do with this vehicle is lift the bonnet and take the dipstick out of the dipstick tube. The connection here is WPS via the vacuum hose into the dipstick tube. Remember that when you power up the WPS, make sure that battery is good. If the battery is not good, the low battery warning will be on, so that would require charge. Switch on, and always remember to make sure that the test port is open to atmosphere, because when you switch on, it will run through the 3 ranges. That's when it's doing its calibration. And for this test, it's range 3. Range 3, minimal. I think we're going for plus or minus 69 millibar, something like that. But the software will set that up, because we go to Automotive, we go into pressure transducers. It's WPS 500X pressure transducer. It's crankcase pressure that we're measuring, and we're going to do this engine running. So again, guided test will load up. There's an image there of how to connect, minimize, run the scope, and we're ready to capture crankcase pulsations. Okay, we'll just go back through the buffer, and there they are. We're always looking for uniformity. So again, all things being equal, even pulsations from each cylinder into the crankcase, contributions to crankcase pressure from each cylinder. Had we got one of those excessive or spikes that were sequential, maybe every fourth event, we could be looking at something along the lines of cylinder wear, severe wear, piston rings all aligned. That's a possible. Something quite catastrophic, actually. We even see sort of crack in a piston, excessive blow-by gas, or even push through the piston into the crankcase. That will most certainly show up. Anything that you spot here that is abnormal is pretty much catastrophic. It's the bottom end of the engine that we need to consider for overhaul or review, certainly further diagnosis. I've chosen to introduce a Misfire on this vehicle, so purely disconnecting one injector while still measuring crankcase pressure, just to show you the effects of a Misfire. Again, we'll keep everything as it was, so the WPS is still in the dipstick tube, it's still range 3. We'll create a reference waveform, so remember this was our good capture from the crankcase. So reference waveform A, so that's been duplicated. We'll run the software, and we'll just see how a misfire affects crankcase pressure in this scenario. Okay, so you can clearly hear the misfire there. Let's just step back through the buffer, and we'll bring these 2 waveforms apart. And the dark blue there, that is our crankcase pressure. The light blue is from the good engine, or the engine without a misfire. And pretty much the conclusion here is that there is not a lot to see in the crankcase pressure. The misfire is because of combustion anomaly, of course. We've disconnected an injector. I was hoping, or would have expected to see something in the crankcase, but it proves here in this scenario with this type of fault that there was nothing to be revealed. But very quickly we've been able to eliminate any escape of pressure, combustion gases into the crankcase via wear in the cylinder or through the piston. As far as this test goes, this could be used during routine maintenance. It's very non-intrusive. It's a very quick test. It's dipstick removed from the dipstick tube, pressure transducer placed into there, and just measure pulsations. Routine maintenance, we could use that perhaps at every service, capturing a signature of crankcase pressure And as this vehicle returns year in, year out, we can look at any deterioration, monitor deterioration or anything untoward in the crankcase. The final pressure analysis we're going to look at is intake manifold. Now, it's pretty non-intrusive. It just depends on the arrangement of the manifold. With this diesel vehicle, I had to take out the boost pressure sensor, just move that aside, insert the tube into the intake hose. WPS is set to range 2. Guided test will follow as our setup. Run the engine at idle, and then we'll capture again pulsations, but this time in the intake manifold. So if we got misfire, be that compression, be it because of combustion, we will see something in the intake. It can be quite a complex waveform to analyse this one, as you'll see certainly with the diesel, an EGR activity. So let's follow the guided test first of all. So again, it's Automotive. It is pressure transducers, the WPS 500X pressure transducer, intake manifold, and intake pressure running. Connection diagram is here and how to connect. Example waveform is loaded. All we have to do is press the start button. We're ready to go. Quick point about the WPS again, make sure that the battery is fully charged. The low battery indicator is off. When you actually switch on WPS, make sure that the test port is open to atmosphere, because when you switch on, it will scroll through all the ranges. That will be performing a 0 calibration, if you like, on each range. We're range 2. We're ready to start the engine and monitor the pulsations in the intake manifold. We'll pause the software there, switch the engine off. As you can see, we've captured something. We need to look at the scaling here. In the guided test, it was set to 1.4. If we scroll up, we'll take that to around about times 8. And there we have intake manifold pulsations. Now, they are uniform. There was no misfire or there's no running condition on here. But it's intriguing as to what we can see. It is slightly below atmospheric pressure. It's if we use the rulers, we can actually measure the negative pressure in the intake is about negative 20 millibars, so very, very small. But what initially intrigued me was the pulsations that we can see that ride on top of the negative pressure, and that's these pulsations here. So what I'll do, again, using the reference waveform, right click, reference waveform, duplicate A. Now you'll see that it's duplicated A, but it hasn't amended the range, sorry, the scaling here. So we'll bring this back up to a factor of 8. There we go. We'll run the same test now, but we'll disconnect the EGR valve, because the peaks that you see riding on this waveform here are pulsations from EGR. So EGR now is disconnected. We'll run the scope, start the vehicle, and compare the pulsations within the intake manifold. You see there that the reference waveform is still on screen. We'll switch that off. We'll come back through the buffer. And there then we have, again, times 8. We have a completely different waveform, different structure. We've lost these rounded pulsations that are attributed to EGR. So as you can see there was a clear difference between EGR connected, EGR disconnected, and we have to be aware of that when we're looking at intake manifold pulsations, because we don't want to assume that the pulsations that we've captured are a fault. We need to also confirm that if we have got something there, is it relevant or attributed to the running condition that the vehicle may be demonstrating. So the light blue waveform here was the intake manifold pressure with EGR connected. The dark blue there, that was EGR disconnected. There's a clear difference. What I'd like to do now is actually, with the EGR disconnected, reconnect whilst the engine's running. So you'll see a change to the structure of the waveform. You'll also notice a change in the engine note. The intake noise increases. There's a definite boom. I hope the mic can pick that up. Before we do, we'll need to create a reference waveform again. So its reference waveform will duplicate A once more. As you can see, it hasn't amended the scale. It always defaults to scale 1, factor of 1. There we are. We'll run the scope. Okay. So you see, colours wise it's a little bit confusing, but we've got the rounded pulsations as EGR operation. We've got the more acute peaks, that's intake manifold without EGR operation. We'll now introduce EGR operation whilst the engine's running. Okay, so the dark blue waveform simulates the upper waveform. We'll reconnect the EGR. Now hopefully you'll hear the engine note change and notice the change on the waveform. There we go. And if I pause Picoscope at this point, switch the engine off, we should be able to come back to the buffer and see the exact point where EGR operation took place. Okay, so let's slide a few of these waveforms just out of the way, because it does get confusing when all waveforms are a similar colour. We'll step back through the buffer. There we go. That was the exact point where EGR began to operate. So here we have our uniform acute peaks, and then here where EGR operation, we start to see these rounded peaks here. So once again, it's important that you are aware of the activity inside the intake manifold. If you can inhibit EGR operation for evaluation of events in the intake manifold outside of EGR, then better. That will improve, certainly remove part of your the complexities of looking at this waveform and allow you to concentrate on things like combustion or compression events. One more check to do now, and that will be to introduce a misfire with EGR inhibited. So we'll just disconnect an injector, disconnect EGR, and compare that waveform. So the final capture then will be number 4 injector disconnected, EGR disconnected. So you'll see the effects of intake manifold pressure and the pulsations in the intake manifold as a direct result of misfire. Okay, we'll pause the software and we'll review that data. So concentrating purely on this dark blue waveform, we can see here that we have this uniformity followed by this smoothing area here, then almost a recovery here, then the same again, 3 events, this smoothing here, 3 events. So again, there's something of concern in the intake manifold now as a result of combustion. It's a tricky one, intake manifold analysis, as exhaust gas pulsation analysis is. What we are always looking for is 4 even peaks of the same structure if all cylinders are contributing evenly to manifold pressure, exhaust gas pressure, crankcase pressure. In the next video, I'll narrate over multiple waveform analysis. So what we'll look at is crankcase pressure, overlaid with intake manifold and exhaust gas pulsation, but then introduce the in-cylinder waveform, so cylinder 4. So we'll actually see the 4-stroke cycle and then relay these different waveforms, or relate these different waveforms together using Picoscope software, but also a waveform overlay software as well. and hopefully we can bring about an explanation as to why these pulses occur, and more importantly where they occur in the 4-stroke cycle. The Pico practical sessions looking at intake, exhaust pulsations, crankcase pulsations, I thought this would be a good opportunity to visit all of these together. So that's 4 pressure transducers, 1 in the exhaust, 1 in the intake, 1 in the crankcase, and also 1 in cylinder. So this is cylinder 4 here. This is the yellow waveform. And it's important to note as well that for the whole of these tests, the only way we introduced disruption into certainly intake and exhaust was by disconnecting number 4 injector. So all that we see here is no more than a misfire, complete misfire on cylinder 4. So valve timing hasn't changed. There are no valve issues. So if you think about poorly seated valve, burnt valve seat, sticking valve, these would all manifest themselves differently in the intake and the exhaust respectively. And of course, bottom end of the cylinder, or certainly piston ring, cylinder wall, all these conditions would you be seen in the crankcase, which in this waveform here is the green. So I wanted to start by just improving a few things visually. What I wanted to do was go to Tools, Preferences, and let's go to colours, and I want to change channel D from the default colour to, let's go to magenta, apply and OK. So now you can see that we've got channel 4 in this magenta colour. I think it's just easier, certainly from a video point of view as well. We'll create a reference waveform as well, because I want to bring in the crankshaft sensor. I want to show the effects on crankshaft speed, velocity. I'm not sure which is the right term for that. Of course, crankshaft speed velocity changes, then so does the piston, and then of course that will manifest itself again in intake and exhaust pulsations. So first of all, let's do a reference waveform, and we'll do channel C. Okay, so we want to duplicate channel C, and then we want to edit, and this is going to be called good crankcase. And colour wise, I see no reason why we can't keep it the same. Let's give it a lime colour. Hopefully that will stand out when we bring all these waveforms together. And there it is, you'll see it in your library. Okay, so let's open the other waveform now, because the important one is to have crankshaft position sensor, and that's this one. Okay, and let's tidy it up straight away, because there is so much going on here. Just to quickly take you through what we have here is, if you look at these intake pulsations, you remember in the video how we had this acute rise here. That was with EGR disconnected, and then if I move along through the buffer, now you see these pulsations have appeared here. These are as a result of pulsations from EGR. Note we're missing a pulsation here, which we'll discuss as we go on. Right, let's increase the screen space. Let's remove all the notes, and let's go to channels. Let's take a number of channels away. We'll take away B, that's the exhaust. We'll take away A as well. Okay, so now what do we have here? We are looking at crankshaft signal, so crankshaft sensor. Yeah. Point to note about this crankshaft sensor on this vehicle. This is the Volkswagen TD5. I think it's the, well, I know it's biturbo. CFCA, I believe, is the engine code. Notice how we have missing teeth every 180 degrees, I believe that is. Let's have a look at that. Let's just pull this rotation ruler out. So this is cylinder 4 pressure waveform. No combustion on cylinder 4, remember, so this is a dummy glow plug installed into cylinder 4, the compression hose, and then the WPS. So we've also lowered compression on this cylinder as well, even though looking at this engine running we were at around about 30 bar. So yeah, in this 180 degrees there's a missing tooth here, and in the next 180 there's another one here. So for every 360 degrees of crankshaft rotation there are 2 missing teeth. So or 2 sets of missing teeth, I should say. So in 720 there are actually 4, look. Okay, be aware of that with this vehicle. But what I'm interested in is the speed of the crank. So let's create a math channel. So tools and math channels, create, and we want crank, and it's channel C, and the number of teeth per revolution are 60. You allow for the missing teeth, so it would be 58, but it will go with 60 per revolution. Okay, let's give this a colour. Let's give it the magenta colour, because that'll be the same as our pressure waveform here. And let's amend this range, because everything was at idle, remember, on this vehicle, so 1000 RPM. We'll click OK, and we should have our math channel here. That looks very messy already. Let me hide the crankshaft waveform, which is C. Let's bring this. I think I've added confusion there by making that the same colour. Let's do something different. So let's edit the math channel. Click on edit. Let's give it a colour that's going to really stand out. We'll go with black. Click OK. Right, now we're doing something. Let's bring that up to 0. These spikes you see here, they correlate with the missing teeth. Let's just zoom in on a group of teeth here. So you've got these missing teeth here, and there's a sudden or an abrupt change in the frequency, or drop in the frequency, sorry, that you see there. Ideally what should have happened with the crank maths is that we don't draw any data where there are missing teeth. Yeah, as you see there. Okay. We'll tolerate that for now. That will improve in the future, there's no doubt. So right click and hide channel C so we can make sense of what's going on here. I'll pull this down so we don't have to dwell too much on these spikes. We'll zoom in on one 4-stroke cycle. Okay, and what I want you to really note here is this stepped view, if you like, or this stepped appearance of speed of the crankshaft. So let's pull these rulers down here. So that's the crankshaft at its lowest speed, 733 RPM, to its uppermost speed, which is pretty much here between these two accelerations here, 952. So just grasp that for a moment. That's a difference in crankshaft speed of 218 RPM from its lowest point here to its highest point here. And this change in speed is what gives us this dramatic, or these dramatic events that take place in the intake manifold and the exhaust system. But remember, we haven't done anything with valve timing. All we did with this vehicle was disconnect an injector. I'll hide this for a second and let's just explain the 4-stroke cycle. So I'm going to hide crankshaft. Okay, you saw the rotation rulers here, 0, 7, 20. Let's pull one more ruler down here, place this on 0. So anything above this line is a positive pressure, Anything below it is a negative. And it looks like we aren't quite on zero with the pressure transducer. Seem to be always below there. Okay, we'll bear that in mind, tolerate that for a second. So this is piston at TDC on its compression. So we've got the compression tower coming up here. This first 0 to 180 degrees of rotation is piston coming down the cylinder. This is what would be the power stroke. It's not power, we call it expansion. There is no combustion. It's just piston rising and falling, acting as an air pump during this 720 degrees of crankshaft rotation. Notice here that we drop into a negative pressure. I'll try and zoom in on this area here. This is called our expansion pocket. And then as small as this is, you see around about this point here that we start to come up. Yeah, there it is. So even though at this point here the piston is still travelling down on its expansion stroke, the pressure in the cylinder starts to rise, and those events are attributed to the exhaust valve opening. So we estimate here that the exhaust valve opened at around about 30 degrees before bottom dead center. If we could be more accurate. If you wanted to see that event with greater detail, a bit of a cheat with a diesel engine is to restrict the air intake, and be careful how you do that. Of course, it's very clear on a petrol engine because at idle the throttle is closed, so we get a very deep, dramatic expansion pocket. But with diesel, we're not so fortunate. Okay, so from this point here, 180 to 360, piston is now rising on the exhaust stroke. And around this point here, there's a multitude of events taking place, and it is very difficult to determine exactly what's going on here. John Thornton has a very, very good video on combustion analysis. Sorry, maybe not so much combustion, but the four-stroke cycle analysis. Take you through WPS operation with Pico, looking at various scenarios with running problems. Very, very interesting video. Okay, so 180 to 360, we know this is the exhaust stroke. Piston would be rising here. Trying to estimate where the exhaust valve closes and the inlet valve opens is a tricky one. The search for overlap is a very interesting discussion on the Pico Auto forum. If you type in search for overlap, guy on there, Fat Freddy, very, very knowledgeable, has done some great work and analysis in this area. Think about what goes on at 360 degrees after TDC on compression. We've got an exhaust valve open, we've got an inlet valve open, we've also got a piston changing direction. So to call a judgment in this area here is challenging at best. You could argue that where I've placed this marker here at 336 degrees after TDC here is that the exhaust valve is closing because we have a slight rise here in pressure in the combustion chamber, and then shortly afterwards we have a drop because now the piston changes direction, we go on the intake. I very much doubt in this area here that the exhaust valve closes. I believe this will be as a result of a pulsation felt in the combustion chamber of cylinder 4 from another cylinder, from a neighbouring cylinder. Because remember, events that you're measuring here, especially in this area, will respond to events in other cylinders because you've got other cylinders pumping away. Those cylinders will have combustion as well. Inlet valve open, exhaust valve open, and piston changing direction. So again, we can't dwell too much on here. What we do know is at this point we start to go slightly negative, because now piston has changed direction, inlet valve is open, exhaust valve will have closed, and now we're on our intake stroke. And our intake stroke, play devil's advocate, I'll say maybe starts around here and would close about this point here, because from 540, that's bottom dead center on the intake stroke, piston is moving down here. After 540 to 720 we start to rise again, and from this point we start to build compression. So the only reason we're seeing a rise in compression at this point, or cylinder pressure, is because the inlet valve must have closed. Okay, so it's a 4-stroke cycle. So now let's bring back the reference waveform. So tools, reference waveform, and we want our good crankcase. Now this was taken from the previous capture where we had 4 pressure transducers. Remember, in this capture channel C had to become the crankshaft, so we had to lose or sacrifice 1 transducer. But I captured this off another waveform using the same settings, same time settings, and the same trigger point. So we can safely say, as near as damn it, that these pulsations, although were lifted from another waveform running the engine at a previous time, because our trigger settings were in the same position here, then the pulsations captured are still relevant. Okay, so there was nothing really to see in crankcase, if you remember from the video. Crankcase pulsations, you know, they were uniform, even with a misfire. Remember, this vehicle is misfiring. We've got a pressure transducer in cylinder 4, that's what you can see here, the magenta waveform, and this is crankcase pulsations. As the piston is falling here on the expansion stroke, this is the pulsation generated from cylinder 4. If this is cylinder 4, then this must be, if you think 1, 3, 4, this would be cylinder 2, back to 1 again, then 3, and then of course the cycle starts over again. Okay, so on that one, not the most entertaining of waveforms, but nevertheless, anything that you see here is potentially catastrophic for the engine, or certainly requires a major repair, because a pulsation, let's say this pulsation was right the way up here and disturbing the one adjacent to it, we could say that we would be looking, well, if this is expansion for 4, 1, 3, 4, this would be expansion for 2, we'd be considering looking at cylinder 2 in more detail. Okay, so let's take away that reference waveform. I think if we go Tools, Reference Waveform, and deselect that, click OK. Next up then, let's have a look at intake manifold. So channels, channel A, and I'm going to step back just a little bit, because that is intake manifold with EGR operation, and let me explain that. I've captured 22 buffers here, and I've mentioned here EGR off to on. So whilst this engine was running, I had the EGR valve disconnected, so no EGR valve operation. Remember in the video when I connected the EGR valve, how the engine note changed, because well, not the engine note, the intake note changed, the boom from the intake increased, and then we saw additional pulsations. So we'll just scroll through. So this is no EGR operation, and that's with EGR operation. Okay, that's this pulsation here and here, but notice this one is missing, which we'll come to in a while. So this is all about analysing these waveforms and trying to determine which is our offending cylinder from pulsations, and this one is intake pulsation with number 4 cylinder misfiring. And I guess we're all drawn to this one here. If we're looking for uniformity, we've got this acute peak here, here, an event here, sort of a deep dish here, and then almost a recovery. Okay. So what's going on there? This is where crank maths comes into play, because when we can see the velocity of the crankshaft and the piston, hopefully it'll make a little bit more sense. So if I right click, channel, bring back crankshaft, and just move them up a little bit. So here we have a dramatic reduction in crankshaft speed, don't we? And let's look at that. Let's bring this ruler down to this point here. I think at this point our crankshaft is at its lowest speed throughout 720 degrees of rotation at 731 RPM. And why is that? Well, here we have a reduction in the crankshaft speed because cylinder 4 is on its compression stroke, so naturally the speed of the crank will reduce. What should have happened here, there should have been a combustion event, so this would have accelerated and would have peaked about here and then would have started to decelerate because the next cylinder, next cylinder 2, would have been on its compression stroke, ready for firing again at this point here. So I hope that makes sense. Here we have a reduction in crankshaft speed because cylinder 4 is coming up on compression, so it's slowed down anyway. Then there has been minimal acceleration and then quite a dramatic reduction because we're starting from a low speed here anyway, and of course cylinders travelling down the cylinder with no combustion, so there's no acceleration in the crank, and also the next cylinder, or 2, is coming up onto its compression, so there is a lot slowing the crankshaft down at this point in time. So keep that in mind, because once the crankshaft reaches its lowest point here in terms of speed, it then has a dramatic acceleration from this low point because of cylinder 2 firing. Remember, this is number 4, so this will be number 2 firing at this point, and we go in a very short space of time. Let's measure time from that lowest point there to the point there. Crankshaft speed increases by 181 RPM in just under 10 milliseconds. So that will have a huge effect on pulsations, won't it, if we think about events in the intake manifold. And that's what we need to focus on here. So I'm trying to keep this as clear as possible. I hope these rulers are not intruding into your view. We're looking for repeat pattern, aren't we? And this is the one that stands out. And why is that? In this area here is all predominantly due to a change in crankshaft speed, piston speed, velocity, because just because number 4 is misfiring, we know that cylinder will reduce in speed, but that will have a knock-on effect for companion cylinders and events taking place, certainly in the intake manifold, because of overlap. So here we have a reduced pull on the intake pressure. Notice here this is a recovery, a good cylinder. Same again here, these two here. That's what we would be looking for on every cylinder. We want everyone to be the same. So this reduced pull again is down to this reduction in speed, because this is cylinder 4 without combustion, so its companion cylinder, cylinder 1, will be on its intake stroke, but without the benefit of the acceleration from cylinder 4. So I hope that makes sense. Cylinder 4 coming down on its expansion stroke, that would be charging down the cylinder because of combustion. That would also force down cylinder 1 rapidly during its intake stroke, and it doesn't have that luxury here, hence we don't get this pull here. Okay, so now we have this smoothing effect here. Now this is quite something. We need to take a real step back and look what's happening here, because at this point, 180 approximately, we said just before, didn't we? We have the exhaust valve opening on cylinder 4. Okay. Now when that cylinder 4 exhaust valve opens, it will not have the pressure and the temperature that it would have had had there been combustion. So there's one difference straight away. Now then, at this point here, this would be the firing stroke for cylinder 2. This is cylinder 4 TDC. This will be its power stroke. Then this will be cylinder 2 on its power stroke. If cylinder 2 is on its power stroke, its companion cylinder, cylinder 3, will be on the start of its intake, or will certainly be on its overlap. So just bear this in mind. The effects that we are seeing here, this smoothing, is the overlap from cylinder 3 and the exhaust gases that would be present in the manifold from cylinder 4 would be felt here because of overlap on cylinder 3. They haven't got that temperature or the pressure. Okay, let me say that once more. This is cylinder 4 opening its exhaust valve in this area here, but without the pressure and the temperature from combustion. At this point here as well, cylinder 2 is starting its combustion stroke, which means cylinder 3, its companion, will be on overlap. So we'll be getting, we'll be sensing overlap from cylinder 3. Cylinder 4 exhaust valve will be open, but without the temperature or the pressure that we'd associate with combustion. And that, I believe, is what we're feeling here. So then moving on, we've got this very sort of deep dish effect here, and that is predominantly because of the dramatic pull acceleration, if you like. Let's have a look at this. This is the crankshaft accelerating dramatically here. This will be cylinder 2 on its combustion at this point, which means cylinder 3 will be coming down the cylinder rapidly on its intake. This area here, we seem to have like a peak, almost like an overshoot there. I'm trying to look at this. Again, I believe that we have this continued increase in crankshaft speed, because remember I talked about this stepped speed. We go low, we build up again, and we kind of plateau around here. So here we have this dramatic increase again. So we've got, that would be, this would be cylinder 4 to, this will be cylinder 1, would be on its combustion. We'd have the overlap gases during cylinder 4. That's this point here. That would have an effect on what we're feeling in the manifold. Right, let's explain that one. At this point here, this is cylinder 4 during its overlap. Accompanied with that is this dramatic acceleration in crankshaft. So I think we've got a combination of cylinder 4 overlap with not the typical temperature that you would expect in the combustion chamber for cylinder 4, have an effect on this overshoot here. So combination of velocity, acceleration of the crank, and a change in dynamics during overlap here on this cylinder. It's minuscule because we almost return to recovery, don't we, at this point here. But if we look at that, here we have uniformity in the crank, because here we have cylinder 1 firing, cylinder 3 firing, and then we come back to 4. So note how this uniformity in crankshaft velocity, piston velocity, matches this uniformity now here in the intake manifold. Realistically, all this mayhem, confusion here is brought about because of a change in speed of the crankshaft, because of a misfire. That would change again, like I mentioned earlier, when we have issues such as burnt valve, sticking valve, different phenomena taking place. And I hope this brings home just how challenging it is, because you've got to think about events happening in neighbouring cylinders, where the overlap is, what cylinder is on overlap, because when you're measuring in the intake manifold, sure enough, you will be detecting combustion events from overlap. And like I said here, we had no combustion in cylinder 4. If I just move on with the buffer, I wanted to show you the EGR operation. Notice the complete change now in the blue. You saw in the video, we have these pulsations. This is where you reconnect the EGR valve. And where are those pulsations coming from? Let me just realign the phase rulers. Okay. So we have, well, let's have a look exactly where we are. And let me try and remove some of the rulers. I think let me remove all of the rulers, hopefully. And I think at this point, speed may not be relevant with EGR. So let me take away the math channel. So all we're looking at now is intake manifold pressure with EGR operation. But I think it is important to bring back the phase rulers, because here I mentioned the start of our combustion stroke is around about here. Sorry, not our combustion, our exhaust stroke. So TDC cylinder 4 on compression, so 0 to 180 will be its power stroke or expansion stroke. There is no combustion in cylinder 4, and at this point here, did we say it was around about 155, 57, something like that, we open the exhaust valve. And look, when we open the exhaust valve, because there's no combustion, there is no pulsation through the EGR valve at that point into the intake manifold, and that's what we're seeing here. So this must be the pulsation then going through the firing order from, well, we'd go backwards, let me go forwards. So if this is cylinder 4 pulsation, this is 2, 3, and let me start again. This would be the pulsation from the exhaust in cylinder 4. The next one then would be 2. Then we'd start again with cylinder 1 and then cylinder 3. So I hope that helps. That looks actually far easier than trying to explain what's going on with the pulsation in the intake manifold because of a reduction in speed, crankshaft speed. Here we're missing this momentary peak, this pulse if you like, as a result of the exhaust valve opening in cylinder 4, but without any combustion, pressure or temperature behind it. Remember, this is EGR valve open, so if the EGR valve is open, we'll feel exhaust pulsations in the intake manifold. And I guess thinking that through, we are getting 2 for the price of 1. We're getting intake manifold and exhaust pulsations, intake pulsations and exhaust pulsations in the intake manifold when the EGR valve is open. So looking at our exhaust gas pulsation, this is exhaust gas pulsation with EGR operation. Remember, these pulsations here are attributed to EGR open, and we're feeling those in the intake manifold. Let's take that away. Sorry, we won't take, we'll just go back through the buffer till we get to a point where the pulsations from EGR, or there is no EGR operation, because that introduces another variable where pulsations in the exhaust are concerned. Keeping variables to a minimum is a must with diagnosis. And you see that we have a uniformity, almost an event here, uniformity, then a dramatic event, a recovery there, back to uniformity. Okay, so this area here, I'd expect that to be an even pulsation. That coincides almost perfectly with the lowest speed of the crankshaft. So here we have number 4 cylinder. At this point here we're about to open the exhaust valve. I am not convinced you would feel, or well, we certainly know as we move on because we'll explain this here, but that will not be directly attributed to the fact that cylinder 4 exhaust valve is opening. That is more to do with the fact that we are at the lowest point of speed of the crankshaft right there. And that is why we don't get that even pulsation here. What we do have at this point here is this sort of dramatic or disruption to pulsation due to acceleration of the crankshaft from cylinder 2, because cylinder 2 fires here. Where we get this, we go from our lowest point to our, not a highest point, but dramatic acceleration. But remember where we are measuring our exhaust gas, the location of our transducer is in the tailpipe. So if we think that we open the exhaust valve at this point here, cylinder 4 exhaust valve open, and the exhaust valve is open throughout that duration. Probably, well, there is an overlap, so we'll go up to 360. So from here, from about 155, something like that, to 360, maybe beyond, exhaust valve is open. During that time, there is a dramatic acceleration in the crankshaft, but also the exhaust gas at that point in time doesn't have the properties of exhaust gas with combustion, so in terms of temperature and in terms of pressure. And that manifests itself as this unevenness, this instability here, this pulsation. Again, moving on, we have another event here, another, not so much a dramatic acceleration, but we still continue to build crankshaft speed. And then at this point here, we come back to what you could say is momentary returning to normal. We've got a conventional event in the combustion chamber. That would be from 4 to 1 from cylinder 3. We'd have an acceleration, typical pulsation in the exhaust, and then things start to go difficult again, or not so much difficult, but they change again, the pulsation changes. Remember, this here was because we reached the lowest point of speed of the crankshaft, which is there. Okay, so all the disruption in here at this point in time is due to the reduction in crankshaft speed and the effects of having no combustion in cylinder 4. Just note how that changes. If I just right click and do a reference waveform of channel B, that'll just place a copy on there. I will have to, increase the scale to a factor of 7. There we go. I think at this point there's probably no need to keep the math channel in place. And maybe lose the time rulers. Okay, but we'll move back through to where EGR operation was taking place. And how do we know EGR operation is taking place? Bring back channel A. Those are those pulsations from EGR. So we know at this point EGR valve is operational. And look how that has changed the pulsations in the exhaust. So this is pulsations in the exhaust without EGR operation. And these are pulsations in the exhaust with EGR operation. So that is something to consider, because here we get a different waveform altogether. Yeah. Remember, we attributed that event, that matched the lowest point of speed of the crankshaft without EGR operation. And I'm sure there's an explanation in there that I don't have, but hopefully this brings home the amount of variables to consider and keeping variables to a minimum. And I had kept a reference waveform of exhaust gas pulsation with no misfire, and that was a reference waveform. So if I bring that reference back, so that's a good exhaust with no misfire. Click OK. Increase the range, scale, sorry, to bring that up, something like ×7. Let me go back through the buffer to where there was no EGR operation and take away the reference waveform. Sorry, take away channel in view, which is okay. Exhaust gas pulsations without EGR operation. Exhaust gas pulsations on the same engine without the misfire. We could actually try and align these better. If we measure the phase between the two, if we try and align that trough with this one here, we've got about 9 milliseconds, so we can delay the reference waveform by 0.008. Yeah, that brings it something like, yeah, so that's what a good pulsation would look like without misfire. You can see the dramatic change when we overlay at this point here. Okay. I think it's probably a good time to just quickly mention a nice piece of software that's out there from Microsoft called Waveform Overlay, or Pressure Waveform Overlay. So go to the Microsoft Store, type in Pressure Waveform Overlays. Here's the software. I think you'll probably recognize it. I'll just minimize it for a minute. We'll open up a file. We'll take away all the pressure stuff for a second, and let's just look at one pressure waveform. This is intake manifold with EGR operation with misfire. Okay. And number one injector. Let's come out. I think you can see there straight away the pulsation in the intake manifold attributed to EGR, misfire from cylinder, whichever one it may be. We'll come to that in a minute. Pulsation, misfire. Okay. So this is the reference waveform intake manifold without misfire. Let me hide that for a second, just get rid of the confusion. The hide feature is a right click. Zoom in on this area here, and this is number one injector, and I've placed the phase ruler, I think, at the start of main injection. May or may not be TDC, it's probably not that important at this stage. It gets us in the ballpark. So how could we determine the offending cylinder from this pulsation? We know that this is sequential, every fourth pulse is missing, but which is the offending cylinder, knowing what we know now? Let's minimize these just so as we get maximum screen space. I'll come back out and grab maybe a few pulsations either side of our 720 so we can see repeat cycle. In Picoscope, click Edit, Copy as Image, go back to your overlay software, right click and paste. So there's your Picoscope waveform. Just pull that out to the absolute maximum. And yeah, use the features in here. How many labels would you like? I would like 5 labels, and I would like to start with cylinder 1, 3, 4, 2, and back to 1 again. We'll pull those out. Remember, this is injector number 1. So injection 3 would take place here, injection 4, injection 2, yeah. When I say injection, because it's a diesel, it'll be combustion, won't it? And back to cylinder 1. We can use the overlay chart here. Number of cylinders on this engine are 4. The cylinder synchronization we're using is cylinder 1. Our firing order is 1, 3, 4, 2. Click go. We can pull this down here and get some shapes so this doesn't intrude. Okay. We can increase the opacity so we can actually make this nice and dark or almost transparent so we can see the waveform beneath. And this is the key to the chart here, and this is the area we are interested in. Cylinder 4, as we know, is our offender, but if we didn't, we could say that at this point in time, cylinder 4 is on its expansion stroke, and at this area here, it goes from expansion to the brown here, which is the exhaust. So here we are on the cusp of opening the exhaust valve. Well, we know the exhaust valve opens on cylinder 4 because we looked in the previous waveform. We knew that when the exhaust valve opens, we get this pulsation, this momentary pulse in the intake manifold. So with that knowledge, if you were presented with this vehicle with a misfire, pressure transducer in the intake manifold, EGR operation active, synchronize on cylinder 1, and then use your overlay chart here to determine the offending cylinder or the cylinder of interest. Okay, hope that helps on that one. It is a very good tool. I do like this. This is pressure waveform overlay from the Microsoft store. It does a lot more. You can bring in your rotation rulers here, 0s and 720s as you would in Pico. So let's bring in another waveform. Let's go back to Pico. Let's go File, Open the previous waveform. Let's have a look at the transducer here. Let's get rid of all this clutter. Remove all the rulers. Hide a number of waveforms. Let's go with all of those. I'm zooming on this area here. So we've just got that 4-stroke cycle. Edit. Copy as image. Let's close that and try opening again because I'm not sure how to get out of that. Pressure waveform overlay. Right click, paste. There's your pressure waveform. I'm trying to grab the 720 ruler in the bottom corner here, but I'm struggling because that is another piece of software that's running. That's allowing me to record this. But here you would have values that you could enter. So that could be, well, let's bring that down to something like what it says on the Pico screen. That would be 0.45. We'll pull that down to 34.94. And then such that when you bring these rulers down here, they will have a value that you'll be familiar with, and a ruler legend that operates the same as well as Pico, so you get the difference between the two, the delta there, min, max. and the same when you pull in your rotation rulers. So this would be 0 here. I'm not sure whether I can drag this out of the way. Right, I've managed to overcome this glitch here with the other software that's running on my PC. So now we have your 0720. We would be able to, I know you can see the little purple square in the corner there. That would be a rotation ruler, so that would give you degrees of rotation. I can't bring that out because again that software intrudes. I'll try and get around that for you. Okay, sorry about that. So now we have rotation rulers that will give us degrees of rotation. Let me bring in these additional markers here. These will give us increments of degrees. So we could place this right on top of the 360 marker there. Yeah, 361, and the delta between the two. To be perfectly honest, if you click on help here, that will take you to a YouTube video that will guide you through this. Bring back these here. These would be your exhaust events if you know categorically where your exhaust valve opens, or using the overlay here, trying to determine 30 degrees before bottom dead center with an overlap period here. You can move these around, of course, and they'll change according to where you place your the shaded area. Some nice features here, like being able to zoom in on an area and then also make that as opaque as you want. So you could actually highlight this area of interest, and then you would file and save that accordingly. I think it's a .png. Alright, that was a huge video. I do apologise. I hope I haven't waffled too much. And any questions, we can catch up at the up and coming webinar, or certainly on the forum or Facebook, whichever. Thanks for watching.
Okay, so to pick up from where Steve left off on the diesel van, we're just going to turn our attention to a petrol vehicle. Now, the setup is exactly the same as it is, but we just wanted to show you the subtle differences between the two engines. So setup is exactly the same. So we're going to take our WPS 500. We're going to make sure it's fully charged up and power on, and allow it to calibrate itself. Now, obviously, allow the test port to be open to atmosphere. You will see the numbers change through the ranges, and when it comes back to number 1, that's when we will know it's calibrated. So following from the guided test, we're obviously going to set up to range 3, exactly the same as we did with the diesel. Now, we already have this set up on this vehicle, so all I'm going to do now is just open up the guided test. So WPS 500, exhaust tailpipe, and we're going to do this running as well. So you'll notice that the guided test will load up in the background. It will give you all the information about how to connect, pretty much what we've just gone through. And the idea is to keep this as simple and as quick and efficient as possible. So we have our reference, if you like, our guide from the guided test. It will automatically set up the time and the scale for you. So it's just a matter of connect to the vehicle and away you go. Now, Steve did mention about the quick and easy way of getting the reference waveform up on the screen. There's something to compare to when you get your results back from your capture. So as before, right-click anywhere on the grid, navigate to Reference Waveforms, and select the channel you want to reference. The only one that's available in this case is channel A. So we can move that up and out the way, and then we can start the test. Something to bear in mind, actually, just as a quick, before you even start the engine, is just to make sure that the reading is on 0. For any reason, if it was to deviate slightly, you could quickly recalibrate the WPS at that point just by turning it off and then turning it back on again. Allow it to do that cycle and you should be good to go. So I'm happy, so we'll start the engine. So as you can see, we have our waveform on the screen. As before, we are looking for that uniformity between the ripples from the pulsations to the exhaust. It's worth bearing in mind that allowing the engine to stabilise and settle is important, as well as making sure that it is warm as well to perform this test if you're performing it whilst running. So at any point, stop the scope and we can turn the engine off. So I'm happy we've got a good capture. Some of the things that could make this slightly different is the different types of exhaust systems that we see on vehicles these days. Bit like the van, we had a twin exhaust system fitted to the back box. Very similar as well with this vehicle. It does actually have a single pipe to a back box and then 2 outlets for it. So you may well find that by plugging one side of the exhaust will help accentuate the ripple. So I'm happy that we've got a good capture. It all looks uniform. We're happy to move on to our next test. Okay, so to follow on from that video then, so we've now got a vehicle that's come into our workshop with a misfire. Customers reported that it's not running as right as what it was. So a quick and easy test is to perform an exhaust gas pulsation pressure test. So simply, without even lifting the bonnet up, we can get an idea of what's actually going on with the engine. So exactly the same setup as before. We're going to use the guided test, but we've already got a known good waveform, so why not use that as well? These can be either from your own collection or from our waveform library. So I've actually already made a reference of a known good. I've got my scope set up, I've got my pressure transducer calibrated and inside the exhaust, so I am ready to go and start making a capture. So we can click start. Okay, so capture on the screen, actually there's not an awful lot that we can tell from that at the minute. So we need to help sort of accentuate that ripple. So we're going to actually start by blocking one side of the exhaust and seeing if that makes a difference. Okay, so we're starting to actually see some difference now that's going on. Within Pico, we can also use the scaling option to help increase and help highlight that anomaly. So we can quite clearly see, so if we stop the scope there, and we can switch our vehicle off. We can now, analysing this waveform, we can quite clearly see that these pulsations as they were before, if we look at our reference at the top, are no longer nice and uniform. Okay, so let's look at a potential fault on a vehicle then. So vehicle comes into a workshop with a misfire. You do a very quick and simple test with the exhaust pressure analysis and we have an anomaly in the ripple. So it's no longer uniform. There is something going on that we need to investigate further. Now, a couple of options here that you could have. You could do a relative compression test. You could look at some other potential issues, fault codes, etc. However, you've got your pressure transducer in your hand. So it may be worthwhile actually going straight to do crankcase pressure analysis. It's exactly the same tooling, if you like, almost with the exhaust pressure analysis. There is an additional hose that we need that's already in the kit. The setup is pretty much the same. So all we're going to do is make sure that our pressure transducer is fully charged. If it has been on, it may be worthwhile now to reset the calibration by powering off and then back on again. Allow the pressure transducer to cycle through 1 to 3 and then back to 1. Now, if we use the guided test on this as well, it will ask to set our pressure transducer to range 3. So we'll do that now, but we'll also load up from the Automotive menu the test for crankcase pressure. Now, to keep things simple, it's come in running. oblique with a misfire. So we'll do a running crankcase pressure test. Okay, as before, we'll get our test come up on the screen. We'll also have a reference waveform. Now, again, we can quite quickly keep that reference on the screen for us to use. And now the next thing we've obviously got to do is get onto the crankcase. Now the simplest way is through the dipstick tube. However, obviously there are some vehicles out there that won't have a dipstick. And if that is the case, then the pulsations will still be at the filler cap area, or if you can get to a positive crankcase ventilation hose, that is also a way into it. Now luckily this vehicle does already have a dipstick tube, so we are going to connect into here. Make sure it's tight and firm, it's not going to fall out. We are going to start our scope, and then if we could start the engine. As you can hear, you should be able to hear there is a definite misfire here. Okay, that's lovely, thank you. And then we can obviously stop our scope and then run back through the buffers. And you can see, again, we're looking for this uniformity of this ripple. If there was any potential problem with the bottom end of the engine, say maybe piston ring failure, or there's something else going on in there, then this will be picked up in this ripple here. So you'll be looking for a slightly increase in pressure if there's excessive blow-by past the piston rings. So that being said, as I said, this is a nice uniform pattern. There's nothing there that's shouting to me that there is a problem with the bottom end of this vehicle, so we can continue on to the next test. Okay, so happy that our crankcase pressure waveform is good. We're happy that there's no anomaly there, so we can move on to our next test, which will be intake manifold. Again, all these tests are tried to be as quickly get to the bottom of how the engine is performing as possible. And if you've got WPS already out and to hand, these tests are the ones to sort of are the go-to ones. So for intake manifold pressure, we are going to use the same adapter we had for crankcase. We are also going to now introduce an adapter, and this little device will allow us to connect to other bits of vacuum piping, but also allow us to go straight into the end of there. Now, with the intake manifold, we need to make sure we're on the right side of the throttle body. With a petrol engine, the throttle flap itself will be partially closed during idle. So we're going to carry on doing running tests because that's how the fault is being experienced. There is it's on this particular vehicle, there's a very nice pipe that comes out directly behind the throttle body itself. So we can just using another bit of vacuum pipe, just literally connect straight in to the intake manifold. Now the pipe that I've taken off is actually for the purge valve for the petrol tank, so we know that it's not going to have any real influence on the actual engine itself. So, connections made. Back to WPS again. Obviously, if you've had it on for a little while, it's certainly worthwhile powering off and powering on again to help it self-calibrate. And once we get back to range 1, we can then load up our guided test. So, automotive menu, pressure transducers, and we are now looking for intake manifold, intake pressure during running. And that will obviously load all our settings up for us, as well as the guided test as well. So we'll minimize that, our settings are all done. In the guided test, it will ask you to set WPS to range 2. So slightly different from the other tests we've done already. Connect in. And that's it, we are ready to go. So we can make a reference of the known good that's on the screen if we want. We can also use the waveform library to bring up another known good for the exact make and model of the vehicle. But for now, we're just going to use that one on the screen. So we will help ourselves by making that as a reference. And then just pull that up there. And we are ready to start capturing. So if we could start the engine. So what you should see is a very good pull down in the intake manifold to start with. You can see already we've got the effect of the misfire, causing a little bit of instability in that waveform. However, as it stabilizes, you could argue there's not an awful lot of information in that capture. If we stop the capture there and stop the engine, lovely, thank you. Now, as we've mentioned all along, actually, the tools within Picoscope can be really useful, and scaling is certainly one of them. So we're going to apply a scale of ×10. So we can just type that in. Obviously, it will disappear off the screen, but we can use the offset buttons that we've got to help bring that pattern back up into focus. So now you can actually start to see that there is something going on within that inlet manifold as a result of that misfire. We're just looking for some sort of guidance and indication at the moment. So we could say that actually we've got a definite sort of rise in pressure at this point, or not as much of an effect from the pull of the piston as it's traveling down the bore in the intake manifold at this point. And as you can see, it sort of steadily drops again before coming back up. Now you could say that we do know there's a misfire, so obviously combustion is not going to take place in that engine, in that cylinder. Now it could be that the opposing cylinder on the opposite side, where it would be on the intake stroke, is not seeing the effects of the speed change from combustion, and therefore actually not creating as much of a vacuum on that side or in that part of the stroke. So we've certainly got some direction now. We are pretty happy that mechanically the engine seems to be okay, which will tend to steer us into another direction. So points now to be thinking about, of course, are ignition and fuel. And as it is, the fault we've simulated on this vehicle is an ignition fault. So by putting that all back together, what we'll do is we'll do that now. So simply pop that on. We can make a reference of this, this pattern as well. So this is a bad pattern now. Again, we will have to change some of the scaling of that reference because it puts it straight back to 1. So if we bring this back up, so you can see there, if we get rid of the initial one that we had, so by going to channels, we can hide that. We can now start our scope up again. And if we could start the engine again, please. Thank you. Now we can see that pull down. And there we go. We have a very nice, stable image. So we are happy that we have rectified the fault. Okay, lovely, thank you. So hopefully that gives some indication as to some quick, simple tests in order to determine whether it's mechanical, ignition or fuel, just by using WPS 500. Thank you.